In this video, I'd like to provide some more context and clarity to the final discussion that we had in our work this week. And I had a third PBL activity prepared. We just didn't have time to get to it. And this helps to explain a little bit about the conservative and non-conservative forces that we're going to encounter in our homework and throughout the rest of the unit. So the first part of the activity that we would have completed if we had time to do this activity was to have you go out on the internet and look for examples of conservative forces and non-conservative forces. I recognize that you may not be super familiar or confident in these definitions yet, but I thought by searching online you might see something that could help clarify this for you. So if you used Google or an AI like a ChatGPT or something like that, you might see some of the following responses. So a few that I found while doing my search were the following. For conservative forces, I saw that electrostatic forces, gravitational, spring, or elastic forces are considered conservative. And non-conservative forces, I found friction or air resistance or drag, tension forces, which are like pulling forces, and pushing forces. Both of those are what we might call our contact forces from earlier in this class. So if these are examples of conservative and non-conservative forces, you might want to further explain these a little bit more. And by all means, if the formal definition helps, you're welcome to find that. But I'll let you kind of do that research and work on your own. You can read through the formal definitions and see if they make sense. Otherwise, I think summarizing these or coming up with a definition in your own words or something that could be presented to, say, a fifth grader to explain the concept might be a good way to go. So ways that I would probably summarize conservative forces are that conservative forces are recoverable, they're position dependent but path independent, and there's this phrase potential energy associated with conservative forces. Now in our class, we're going to be spending a lot of time talking about gravitational potential energy and a little bit of time talking about spring or elastic potential energy. We won't be talking about electrostatic potential energy here, or forces for that matter. So when we talk about the idea of recoverable or position dependent, let's do this in the context of gravitational potential energy or forces due to gravity. If I were to take an object and place it here, sitting on a table at position A, and I were to raise it up to position B, I've now increased the gravitational potential energy. We can calculate that with this little formula here. And so it has more potential energy, but the position of the object, whether it's at A or B, is what determines how much potential energy it has. It wouldn't make a difference if I were to take object A and carry it around with me like this and follow a path, like a squiggly line path up to position B. That doesn't matter. The location, or in this case the height above some reference point, that's what determines the amount of potential energy associated with gravity. And if I were to start at position B and head towards position A, well, if the object were to fall from B straight down to A, or if it were to roll, say, on a track along this dark line here, that object would lose some of its potential energy because the height quantity is reducing. But we could simply recover that by raising that object back up to point B. We can essentially recover the amount of energy that was consumed during the act of utilizing those potential energies and converting those into work and force. But on the other hand, when we talk about non-conservative forces, this is where losses occur. These non-conservative forces are path dependent, and there is no potential energy associated with them. Let's consider that object again, A and B. If we're taking an object and placing it at point A, and we're moving it to point B, this time instead of this being a lift and us considering the gravitational potential energy, let's suppose we had to apply a pushing force to move A up to B. And if this was sliding, for example, if I was pushing an object from A to B and there was some friction involved, well, the amount of energy that I would lose due to friction fighting against this push is a certain amount if I follow this path. But if I were to push this object along that curvy path again, Well, I have a much longer distance to experience those frictional forces. I have a much larger distance that I have to push the object and apply that force over a particular distance. So the energy necessary in this particular event depends on the path that I take to get from point A to point B. And as I arrive at point B, whether I take the short path or the long path, I've lost the energy that I've put into the system to get it there. Now that I'm at position B, I don't have this potential energy that can be undone and return me back to point A. There were lots of forces that were lost along the way. So while those might be some generic descriptions of conservative versus non-conservative forces, it's really just going to take some time to work with the formulas and see some examples to really make this make sense. So if you're still a little bit confused as to the meanings of these definitions or how they might be used, I understand. Just work through some of these problems, consult some additional videos, maybe do some more reading and practice on your own, and these will start coming to you with a little bit more of these exercises. Now, on the back side of what would have been the handout for PBL number 3, I have a series of equations that are derived from this notion of conservative and non-conservative forces. And with any luck, this might help explain some of the work that we're doing as well. So if you can follow along with this part of the video, that would be great. If you're still a little bit lost after it, I understand that too. But we're actually going to be referencing these formulas that I establish on the right-hand side throughout our homework and for different practice problems in the next week or two. So we'll start off with the comment on the left and kind of summarize it with a formula on the right. In most situations, or in a regular situation, both conservative and non-conservative forces can act on an object simultaneously. So therefore, the amount of work that's being done on an object or to an object can be computed by examining or viewing the net external force or the net force. So we would then say that our net amount of work, as it is a sum of all individual forces that are potentially doing work or that are doing work on an object, the net amount of work is the result of the sum of the work done by conservative forces and the work done by non-conservative forces. We use WC and WNC to represent work done by conservative and non-conservative forces. In class, we showed that the work done by a conservative force is the opposite of the change of potential energy. We were starting to talk about the weights in a clock that might be used to give power to a clock or energy to a clock for a certain period of time. So we note that the work done by conservative forces in this part of the equation could be changed to the opposite of the change in potential energy. Work is, in fact, just a measure of a change in energy. And since that's the case, if work is equal to the change in energy, then the net amount of work that's being done, while conservative forces are connected to and responsible for our change in potential energy, the net amount of work that's being done, according to our work energy theorem, would be our change in kinetic energies. So by substituting these quantities in place of our net work and our conservative work, our conservative force work, we have this expression here, and now we can actually isolate the work done by non-conservative forces by simply adding our potential energy to the other side. And so we have this new definition now that while net work is the sum of conservative force work plus the non-conservative force work, the change in kinetic energy is the sum of the work done by non-conservative forces and the opposite of the change in potential energy. So therefore, work done by non-conservative forces by itself would simply be the change in kinetic energy plus the change in potential energy of the object. Now, since an object can possess both potential and kinetic energy simultaneously, so it can be moving and have a certain amount of energy, it could be elevated and have gravitational potential energy, for example, or it could be pressed up against a spring and have spring or elastic potential energy. So since an object can have both of those simultaneously, then we simply say that the sum of those energies at any given moment is the total mechanical energy. So in general, E, which is going to represent our mechanical energy in this class, is literally just the sum of any kinetic energy and potential energy that an object possesses at a given point. That will be helpful to note when we get to the bottom of this discussion. That way we can talk about the amount of energy at the beginning and the end of an event if we can calculate the energy at any given moment, say the initial total energy versus the final total energy. But if we take a moment and return back to the non-conservative, force work section here, then we've got some interesting math that we can do to rearrange some of these expressions and obtain something, a new formula that might be particularly useful. So if we're saying that work done by non-conservative forces is the sum of the change in kinetic energy and the change in potential energy, that's what we were saying up here, then we also know that kinetic energy, at least the change in kinetic energy, would be the kinetic energy that an object possesses at the end of an event minus the kinetic energy that the object possessed at the beginning. And same thing with potential energy. The change in potential energy is the amount of potential energy at the end of the event minus the potential energy that it possessed at the beginning of the event. If we rearrange and group these expressions using our associative property of addition, we might see that, well, this positive KEF plus positive PEF, well, those two can go together. So kinetic energy final plus potential energy final. And then we have this subtraction of kinetic energy and a subtraction of potential energy. Both of those contain a subtraction sign, so if we factor that out, we can put it in front of a grouping symbol. And now we have kinetic energy initial plus potential energy initial. The sign changed here because we factored the negative signs out of both of those terms. Okay, well, that might look familiar to you. Kinetic energy plus potential energy, well, that's what we just called our total energy. So we'll call that energy final, since this is the total energy possessed by an object at the end of an event. Both of those are the energies at the final position. And then the kinetic energy initial and potential energy initial sum together is the total mechanical energy initial at the beginning of the event. So therefore, we can now say that the work done by non-conservative forces is simply just the change in mechanical energy. Now, if we're working in a system or with an object that experiences no non-conservative forces, it's a strange way to say it, but if we have no non-conservative forces like friction, air resistance, tension, thrust, sound, if those items are not present in the system, then then that's our way of saying that we have no non-conservative forces, therefore no work done by non-conservative forces. And that leads us to some interesting ideas, or in particular a specific principle, the conservation of energy, which a lot of us have already heard of before. And so a little bit earlier, we were reminded that the network done by the network done onto an object or on an object is the change in that object's kinetic energy. We've already utilized that once, and we've seen that explained before. So if we remember that, we know that the network done by or on an object is equal to its change in kinetic energy. We know that those two quantities are equivalent. Then by a transitive property of sorts, we can say that these two are both equal to the change in kinetic energy, where mass velocity, 1/2 of mass velocity squared, is the kinetic energy at one point, in this case the final position, and then the kinetic energy at the initial position. So the difference between those two is also the change in kinetic energy. But if we're in a situation where only conservative forces are doing work on an object, if we're in the absence of non-conservative forces, like we started to indicate up here, then the network that's being done is responsible for, or is only being accounted for by work done by conservative forces. So therefore, we would say the work done by conservative forces is equal to the change in kinetic energy. So this network is the change in kinetic energy, but now we're saying without any non-conservative forces, then the work done by conservative forces has to take up that change in kinetic energy. But if the work that's being done by conservative forces is observed and measured, we know that the work that's done by conservative forces reduces the amount of potential energy. So we can say that our work done by conservative forces is the change in potential energy, the opposite of the change in potential energy. We lose potential energy when we're doing work with conservative forces. So we can now say that the opposite of the change in potential energy is equal to the change in kinetic energy. And to make this equation look a little bit more appealing, we'll just put these two together on the same side of the equation. And the change in kinetic energy plus the change in potential energy ends up equaling 0. And if we break apart the change in kinetic energy and potential energies again, we might recall that we have the kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. All of that has to equal 0. Now, if we collect some terms like these initial terms that are negative and add them to the opposite side of the equation, we now have this expression here where our kinetic energy final plus potential energy final is equal to our kinetic energy initial plus our potential energy initial. And again, we're saying that the sum of the kinetic and potential energies is just energy in total, our total mechanical energy. And so this is our way of saying that the energy at the beginning of the event must be equal to the energy at the end of the event of an object, provided that the work that's being done on that object is that done by conservative forces. But that's a pretty big assumption that only non-conservative forces are doing work. That would imply that we have to ignore things like air resistance and friction and things like that. So in an introductory physics course, this is what we often do, is to maintain these nice convenient formulas, we ignore some of these other features. Now, in reality, we can incorporate those functions, or we can incorporate those features or those other components of the equations. It just makes things a little bit more challenging. So if we focus on these ideal situations, ideal conditions, then we see how the formulas tend to work and how they behave. And that leads us to a little bit better understanding of the conceptual ideas behind the situations. So, not 100% sure if that helps much, but hopefully you can see some of my logic there and take some pieces away from that. I think at this point I'm going to jump over to a couple of the homework problems and talk about them for the last little bit of this video, because I think numbers 7 and number 8 especially are good discussions for our conservation of energy and our work energy theorems, our work energy principles. So we're going to take a look at that. Now, by the way, I did post this this image online. These are some hints for us to consider while working on the homework. For number 7, I do like this notion of non-conservative forces doing work, how that's the change in energies. And then similarly, we use that for number 8, but we also have to incorporate an angle component with that as well. Although maybe that's not the case. Let me think about that. I'll think about that once I get there, because we're just dribbling a basketball vertically here for number 8. But we'll see what that looks like here in just a moment. Let's talk about number 7. In number 7, we have a student that's sliding down a water slide, and this student has a mass of 83 kilograms. Is starting at a height of 11.8 meters above some equilibrium point, and we have kinetic friction acting to slow her down as she's going down the slide. Can we use some work and energy theorems to establish how fast she was going at the end of the slide? Well, I would argue yes, and a key takeaway here in this problem is that we're facing a frictional force that's doing work. Now, friction is a non-conservative force, so if I look back at this series of equations that we just established a minute ago, I know there's a lot of them and we rearranged them many times, but I want to focus on this guy for just a second. Work done by non-conservative forces is equal to the sum of the kinetic and potential energies, or the change in kinetic energy and potential energy. The amount of work that's being done by a non-conservative force is equal to the change in kinetic and potential energies of an object. So with that in mind, if work done by non-conservative forces is the change in kinetic and potential energies, then I think we can use that to compute our final velocity. I'll show you what I mean. Well, here again, our work done by non-conservative forces is equal to the change in kinetic and potential energies summed together. And if we note that our change in kinetic energy is the difference between the kinetic energy at the end of the event and the beginning of the event, same thing with potential. And we can again substitute in the equations that compute those values for us. Now this is particularly interesting because in the problem we're taking note that at the top of the water slide this student has no initial velocity. So if she has no initial velocity, then there's no kinetic energy at the beginning of this event, and this whole term can disappear. Similarly, and since this student has zero height left over when they reach the bottom of the slide. Now I know there may be some height above some other point, but in the context of this problem, this person's reached the bottom of the slide. There's no more potential energy or no more height for her to utilize the gravitational potential energy here. So we're going to say that the height being zero generates no more potential energy at the end. And so now we've already simplified this formula quite a bit by making these big terms disappear. And after we rewrite this just to see how much more simple the equations become, then we can note that our job is to find the final velocity of this person at the end of the slide or at the end of the event. And so that's our VF quantity that we're going to try to isolate now. And so with a little bit of manipulation, we can add this term to the left-hand side. I chose to multiply by 2 to eliminate the 1/2 fraction here, divide by mass, and then use a square root to isolate everything else. And we've got our final velocity is going to be the result of this computation. And so after substituting our known quantities from our given information and using a calculator, and reducing for significant figures, I see that we have a result of 8.65 meters per second. And do remember that it's your responsibility to check your units on this to ensure that they work. If this was the formula that you simplified to, then I would use this formula to verify that the units will indeed produce a meters per second quantity. If you don't show that on this test for this unit, then points will be lost. All right, so moving on to question number 8, I think this is again another good example of the work energy theorems. So in this problem we have a basketball that has a mass of 0.6 of a kilogram. It's starting from a height of 1.05 meters and it rebounds to a height of 0.59 meters. We would like to know how much mechanical energy was lost during the collision with the floor. Now, they're using the term collision here, and that's fine, but collisions themselves have their own series of formulas and equations that go with them. We're going to talk about those more in Chapter 8. But what we're really trying to emphasize in a problem like this is that if a basketball is starting at one height and it falls, and then it rebounds, it's trying to regain the potential energy that it had from the very beginning, but there's going to be some amount of loss. And so this amount of difference here can be accounted for by energy loss. And so that's the math that we're effectively going to compute with this particular problem. So here we go with it. We have a mass of 0.600 kilograms. We have an initial height of 1.05 meters. We have a final height of 0.59 meters. And I would likely use the same formula that we had just a minute ago. The work done by non-conservative forces is the change in kinetic energy plus the change in potential energy. Now, what's interesting here is that the kinetic energies are both going to be zero, and I'll try to explain why. Again, if the basketball is here at this position and then we drop it and it bounces back to this position, the event that we're trying to describe is the event from here, from starting point when it was at its highest point to its next highest point after the bounce. And at that moment, right, this is our initial position, this is our final position. At that moment of release out of the basketball player's hand to the point where it reaches its peak height after the bounce, the velocity ends up being zero. So at the very beginning of the event, it had a velocity of zero, and at the very end of the event, it had a velocity of zero. So it had no energy associated with kinetic energy. So try to wrap your head around that concept for just a second. The event is right at the moment that the ball is released, basically, and then the moment that it reaches its highest point again. Because I don't think it said anything about. Yeah, it said it was dropped. It wasn't dribbled in this first case. It was literally just let go and dropped. So there was no input energy throwing that ball down. So in this case, the work done by non-conservative forces, gravity, is the change in potential energy. So we might describe that as PE final minus PE initial. Sorry, I may have misspoke a minute ago. Work done by non-conservative forces would be the change in potential energy. If these two aren't equal, then there has to be a non-conservative force at play here, aka the push or the impact with the floor. So our MGH final minus MGH initial should suffice. We've got some common factors, so if you wanted to factor those out, that would be totally fine. This might help with your unit analysis when you're going through that. But we'll substitute our quantities, 0.6 kilograms, 9.81 for gravitational acceleration, and then our heights of 0.59 minus 1.05. Now take note, the formula was given to us in terms of g, so I am using a positive 9.81 for g acceleration. And then we are subtracting final position minus initial position. The final position was lower than the initial position, so we should get a negative result. And the answer does come out to be negative 2.7076. And with significant figures, we would call that negative 2.7. And the unit ends up being joules. So we have lost 2.7 joules of energy, of potential energy, and that loss of energy is accounted for by the non-conservative forces that have done work on the basketball. So the energy of the ball that was transferred into sound or maybe heat at impact, you name it, any energy that was lost from the potential sense but got transferred into something else, this is the total amount that we've now lost. Now in part B, I think this is where the basketball player was actually was dribbling the ball, so there's an extra force at play. So the player still releases the ball at 1.05 meters above the ground, but also has an external force acting on it. And so that external force was applied for a distance of 8/100ths of a meter. So their hand must have been in contact for a certain amount of distance. The player compensates for the loss of mechanical energy because the ball is able to return back to the maximum height. So the question would be, what was the magnitude of the force that the player has put into the system? Well, it's going to be helpful to recognize that we already know how much work is being done. We know that this player has to put in 2.7 joules of work to make up for that loss of potential energy. And we'll also note with our old traditional definition that the work that's done by a pushing force, which we'll now call a non-conservative force, must be equal to force times cosine theta times d. That's the definition we've been using in class, where force in the direction of the push multiplied by the distance or the length that we were in contact with the object will give us the total amount of work that's computed. Now we could use theta values on a unit circle and maybe make some sense of all of this, but I'm afraid that if we do commit to the unit circle right now and we think of this downward push, the basketball player is pushing down to get the ball to move down. Well, now you're going to be using an angle measure of 270 degrees. Cosine of 270 is 0, and so that's going to mess with our computations just a little bit. So rather than worrying about forces in a two-dimensional direction, I'm just going to think about forces in a one-dimensional direction, forward and backwards. So if the energy that was lost was a negative 2.7 joules, then I know that the energy that this player is putting in is a positive 2.7 joules, and the player, if we're just pushing the ball forward, if we think down is now forward, I'm just going to say that this is a 0-degree angle. So this is our now forward direction, and then the bounce or the rebound we can consider our backwards or negative direction. So here we go. The non-conservative, we're just trying to solve for f, and cosine of theta ends up being 1. So we're now taking note that the work done by the non-conservative force is equal to force times distance. We're trying to solve for d, for f. So the force is the work done by non-conservative forces divided by the distance that the work was being applied, or that it took for us to complete that work. And so we have positive 2.7 joules divided by a distance of 0.08. When we divide those two, we end up getting 33.8 newtons of force. And I guess we only have 2 sig figs, so I better call that 34 newtons of force. So that player has to push the ball with 34 newtons of force in order for it to return all the way back to its starting position. All right, so there are a few examples of our work and energy theorems, this notion of conservation of energy and how that might be applied to some real-world situations. So hopefully that helps some things a little bit, and we'll continue to discuss them more as the weeks progress. Thanks for watching.